All right. Well, before we get started, are there any questions on anything? We're good? Okay. Everything's good. All right. Well, glad to hear. All right. So today we will talk about Chapter 11. Okay. And the topic of Chapter 11 is Anova, which stands for Analysis of Variance. So that takes the Anova. And specifically, we will just learn the most basic form called one-way Anova. Okay, so this is the most basic form from Anova. Yes?
In academic conversation, when you're talking amongst your colleagues, do you say, like, oh yeah, I did an Anova on this, or do you say, oh, I did an analysis of variance on this?
You can just say Anova, and they'll know what you're talking about. Yeah. And so, I would say if you're interested in more statistics, you can often take a course dedicated to Anova, and it will cover all sorts of stuff. And I would say that's probably like a good next step. So, and then next week we'll cover regression. And again, if you're interested in more statistics, I would say a good next class would be either a class on Anova or a class on regression, where you delve a little bit more deeper into these topics. In this class, which is a little bit more of kind of a survey of all these different things, we'll only spend 1 week on this, but you can definitely take an entire course on it, or even more. Generally, a course on Anova will be called Design of Experiments. Which is its whole own subject in statistics, but Design of Experiments and Anova go hand in hand. They are you set up the experiment in the design part with the idea of making your analysis meaningful. Okay, so yeah, that's kind of the principle in Design of Experiments. Is you're thinking ahead to how you're going to analyze the data, and with that in mind, you try to set up your experiment so that the information is collected in a good way. Okay. All right. So exactly, what does Anova offer that the other experimental methods don't? Okay. So we use Anova to compare the means of multiple independent samples. Okay, so it's similar to a t-test. Contrast this to a t-test where we are comparing the means between two samples. Anova allows us to compare the means of more than two samples. Okay, I mean, you could use Anova for just two samples, but in that case, probably the steps for a t-test are probably recommended. But Anova allows you to compare more than two samples. Okay, so contrast to a t-test where we compare the means of two independent samples. Okay, and so the the example in the book, example 11.1.1, and the text talks about different organic methods for controlling pests, and apparently you can implement a bunch of things, such as nematodes or wasps, or a combination of nematodes and wasps. I'm not even sure what nematodes are, but apparently they're
like very, very small.
They live in the soil, apparently. So apparently these are ways to control pests, and then you've got bacteria, and then the control group. Okay, so it's just organic pest control methods. And basically it had 5 different treatments. 5 treatments, okay? So, and one of them is a control, all right? And then so you will end up with you end up with 5 sample means and 5 sample standard deviations. So how can we effectively compare these sample means to each other? And so one method that might come to mind is just do a whole bunch of t-tests. And in terms of the amount of work, to do it manually would be a lot of work, but then to do a bunch of t-tests on the computer, it's not so bad. You just say t-test this and this, okay? And it's not too terrible, right? But we would run into a problem. So we could have the first test, the null hypothesis, could be is mu1 equal to mu2, and then the next test could be mu1 is that equal to mu3, and then the next one could be is mu1 equal to mu4, and so on and so forth. And you would have, is mu1 equal to mu5, is mu2 equal to mu3, so on. And I think there would be a total of 10 different tests, okay? The 10th test would be is mu4. The null hypothesis would be is mu4 equal to mu5, I think, okay? So we would have 10 tests in total. I should say 10 t-tests in total, okay? So this would be, to do a bunch of t-tests. Can you guys think of a problem that could arise with performing 10 different t-tests?
Other than the labor?
Yeah, so let's just say the labor is not too hard, because we could write a script on a computer and say, here's 5 different means, do all the combinations of t-tests. So the labor is, with computers, it's not too much of a problem.
How do we say anything about how they all relate to each other?
Yeah, that also, yeah, that is a little bit of a wrinkle, but the problem isn't so much there. Okay, so let me tell you where the problem comes up is that every time you, so let's say, so we'll say, the problem with multiple tests, or we'll just call this the problem with multiple comparisons. Okay, so with 5 samples, you know, we would have 10 t-tests. Okay, and what's going to happen here is, you know, with each t-test, what is the probability of a type 1 error? Okay, it would be equal to alpha. So let's say we just used kind of the default level of alpha equal to 5%. Okay? So that means the probability that we don't commit a type 1 error would be like 95%. Okay? And so basically you've got 10 tests, and every time you perform a test, you have a 95% chance that you'll not make a type 1 error. Okay, but if you're playing the quote game 10 times, then your risk of committing a type 1 error over the course of 10 tests is now much, much higher. Okay, so the probability of type 1 error is equal to alpha. So, you know, after performing 10 tests, the probability that you have committed a type 1 error is much higher. Okay, and this is a problem that just exists in statistics. We haven't really found a solution with trying to trying to avoid this. Okay, this is just called the problem of multiple comparisons. And so, you know, after performing lots of these t-tests, it's much higher. And so, you know, kind of naively, if we say, well, each time we perform a test, there's a 95% chance that I won't commit a type 1 error, and I raise this to the 10th power, you know, the probability that I get through is now only about 60%. Okay, yeah, so now there's about a 40%. This is not entirely accurate. But there's now about a 40% chance that I've committed a type 1 error. Not entirely accurate because this is assuming all of the tests are independent to each other, but as Michael pointed out, you're using the same data over and over, and so they're not quite independent, so we can't just raise it to the 10th power, but the idea that we have a much higher risk of a type 1 error is now there. Okay, and so ANOVA, by using ANOVA, we have one null hypothesis, and so the overall probability of a type 1 error is just our alpha for the test. Okay, so with only one null hypothesis, okay, and the probability okay. The downside of ANOVA is that you lose a bit of specificity. Okay, so with a bunch of t-tests, you could find out, oh, it was sample 4 that had the different mean. Okay, because sample 4 versus sample 2 was different, sample 4 versus sample 3 was different, sample 4, you know, stuff like that. With one-way ANOVA, the end result is just your null hypothesis will be, are all of the means the same, and the alternative is at least one of the means is different. And so the conclusion you'll get from ANOVA is just something is different from the others, and it won't tell you exactly which one it is. You might be able to suspect it from the data, but ANOVA itself will not tell you it is this one that's different. Okay. So the trade-off okay, so the null hypothesis in ANOVA and then the alternative okay, so ANOVA cannot tell you which mean is the mean that is different. Okay. Is this okay? So let's try out an example here. Okay, and so I think maybe the best way to explain ANOVA will be to just work through an example, and I'll and explain things along the way. Let me. I'm going to just pull up a table from our textbook. Let me pull this up here, and this is going to be like. Here we are. Okay, and so here in this example we have, we're putting, I guess, a bunch of different lambs, like 12 of them, on different diets, and we want to see how much weight they gain. Okay, so we want to know how much weight these lambs gain after you know, a couple weeks on these diets, and so we had 3 different diets. And on diet 1, you know, a lamb gained 8 pounds, another lamb gained 16 pounds, and another lamb gained 9 pounds, for an average of 11 pounds. Okay, now on diet 2, these are the weights, different amounts of weight that the lambs on diet 2 gained, and the average weight gain there was 15 pounds. And under diet 3, you know, there were 4 lambs, and the average weight gain was 12 pounds. Okay, and so the question is there a difference in the amount of weight gain between the different lambs here? Okay, so you know, we have lambs on 3 different diets. You don't really need this row that says sum, but it's there, okay? And so when we write our hypotheses, there's a couple ways we could do this. Excuse me. Thank you. Okay, so our null hypothesis can be written this way. We could say mu1 is equal to mu2 equal to mu3, saying that all of the means are the same. Okay, and then the alternative would be at least one of the means, at least one of the population means is different. Okay, so that's one way we can write this. There's another way that can be we can write this, and this is kind of in the form that each kind of alternate form. So this works quite well for one-way ANOVA, okay, because it's simple. But the alternate form is that we can say each observation y is made up of different things here, okay? And we could say each observation y comes from kind of this overall mean plus the effect of being in a group plus individual differences. So we would say this is the overall mean, and this is the, quote, effect of the group. So this would be, in our case, would be effect of the diet, and this would be individual differences. Or what we might call the residual difference. Okay, and so we'd say, okay, you know, the overall average of all of these, all 12 of these lambs is something like, the overall average is like 13 pounds if we average all 12 of these numbers together. And we could say, okay, this lamb weighed only 8 pounds, okay? We can say part of it, so taking you know, the first observation, so one lamb gained only 8 pounds. Okay, and so we would say y, the 8, is equal to the overall group average, which is 13 pounds. So 13 is the overall average. And then if we compare the group's mean, diet 1's mean, diet 1 is 2 pounds less than the group average. So we would say the effect of the diet is a -2, okay? And so, so that brings it down to 11, and then we would say, and this lamb happens to gain even less than his group's average, and we would say a -3, okay, is the individual difference, okay? And so this would be the diet effect, and this would be the residual difference, okay? And so we would say this is why this lamb gained only 8 pounds, okay? Yes?
So overall, you took the mean of all three.
I took the mean of all 12 numbers, okay? And so I'll illustrate this on the next page, okay? But so the overall mean is the mean of all 12 numbers. It's not the mean of 11, 15, and 12. It's the mean. It's the mean of all 12 numbers. It's not 11 plus 15 plus 12 divided by 3, and I'll explain the difference there. Okay.
And then the -2 you said was from
The fact that 11 is 2 pounds less than the overall mean of 13. Okay, so being in diet 1, according to the data, puts you at a kind of like a 2-pound disadvantage. Okay? So this is, we would say this is why the one lamb gained only 8 pounds, okay? And so in the alternate form, your null hypothesis would be written this way. We would say tau 1 is equal to tau 2, which is equal to tau 3, and all of these have an effect of 0. Okay? And then the alternative hypothesis would be at least one is not 0. Okay. So these are effectively saying the same thing, okay? As far as one-way ANOVA goes, this form is probably the most intuitive and easiest to understand. The group means are all the same, okay? But as if we were to ever do more complicated ANOVA, like two-way ANOVA or randomized block ANOVA or something like that, it becomes much more difficult to, well, we can't use this form anymore, and we would rewrite our hypotheses in this form, okay? And so I kind of show this to you now because who knows, in the future you might do ANOVA, and you should be familiar with this form as well, okay? But effectively, they will perform the same test. Okay, so let's talk about this thing. Okay, so I've got this data here. Okay, and then so the overall mean would be gets the symbol y double bar, sometimes called the grand mean. Okay, and in this case, this would be the average of all the observations. Okay, and so so symbolically, what this looks like is we would say add up all of the observations in a group and add this up across all groups. Okay, so you get this double sum. So add up within a group and add up for all the groups. Okay, add within a group and then add all groups. Okay, and we would divide this by basically the sum of all of the group counts. Okay, add all group counts. Now this sounds much more complicated than it actually is, this thing. It's really just, if I were to add up all 12 numbers here, I would get 156, and if I were to count up how many numbers I have, I would have 12. Okay? And then I would get an average of 13. Note that 13 does not equal 11 plus 15 plus 12 divided by 3. Okay? So 11 plus 15 plus 12 divided by 3 is 12.67. Okay, so this would, so that is not the same. Okay, this form would require having all of the things available. Sometimes you only get the summary information. Okay, so another way to get the grand mean, and this is probably going to be the formula that you end up using, is you would take each group mean and you would multiply it by the group count. Okay, so we would take 11 times 3. We would take the count of a group and multiply it by its group mean. Okay? And we would add those up, and then we would divide by the sum of all the different n's here. So in this case, we would do 3 times 11 plus 5 times 15 plus 4 times 12 divided by 3 plus 5 plus 4. And this would give me 156 over 12, 13. Okay, so it's kind of like a weighted average of these sample means here. Okay, so that's what effectively what we want. Okay. Rather than just weighting these all equal. Okay, so that gives us our grand mean. Okay. Okay, so then with ANOVA, we call it the analysis of variance, and the reason why we call it the analysis of variance is we think of kind of the total variance that is present within our data, and we're going to try to split it out into 2 parts. Okay, so so in ANOVA, we look at the total variance in the group, and we try to, you know, break it apart. Okay, and the 2 parts that we're going to try to break it apart is into basically group variance because of group differences, variance due to group differences, and variance due to individual differences. Okay, so what I mean by that is that, you know, when we look at all 12 of these numbers, we have 12 different lambs, and they've gained different amounts of weight. And we could, if somebody asked us, you know, imagine a child asked us, you know, why did the lambs gain different amounts of weight? We could, one answer that's simple and will work is just, well, all lambs are different, and so they're going to gain a different amount of weight. Okay? And that's always going to be true, because there's always going to be individual differences present, and that will explain part of why the lambs gain different amounts of weight. What also might be true, though, is that the lambs were on different diets, okay? And that might contribute to also why the lambs gained different amounts of weight. And so we're going to try to break apart the total amount of variance into parts that are because of the lambs were on different diets, plus also the fact that there are individual differences, okay? You know, you imagine a child asking, you know, why are some people tall and why are some people short? We can just say, well, everybody's different, and that's why some people are tall and some people are short, okay? We might be able to say, well, also, you know, this sounds silly, but, you know, there are also boys and there are also girls, and in general, you know, men end up taller than women, and so that's why people are different heights, okay? There's different sexes that exist in the species, plus the fact that there are individual differences between people also are a factor. And we could try to separate out the total amount of variance into these different parts here, okay? So do you recall what variance is? Okay, so yeah, variance is the standard deviation squared, but what did we kind of say the variance is? So yeah, that is true. So we can say variance is kind of our formula for the standard deviation squared, but you know, variance can be thought of as the what? Kind of the quote-unquote average. What? Average squared distance from the mean? Kind of? You guys kind of remember that? Okay, so we can think of the variance as the, quote, average squared distance from the mean. And I have the average in quotes because we divided by n minus 1 rather than n. Okay? And variance overall is a measure of spread, right? So we're looking at how far are the points from the mean. So this is kind of, we add them up and then we divide by n minus 1. But what we're adding up is we're taking each point y and we're subtracting off the mean, and we are squaring it. Okay? Okay, so in the context of all of these data points that we have, we can think of the total variance would be, we would take each point and we would subtract off the grand mean and we would square that, okay? And then we could add them all up and divide by n minus 1. Okay. Let's just focus on the total squared distance from the mean, okay? So instead of dividing by n minus 1, we could just look at the numerator, because effectively this is gonna exist in all of our things. So we can get an idea of the spread just by looking at the total squared distance. Okay, and so this is the numerator is often called the sum of squares. Okay, so the numerator, which is taking each point and subtracting off the grand mean, this is just going to be called the sum of squares. Okay, and so this will be the sum of squares if we do this for all 12 points. Okay, this could be called sum of squares total, for basically all 12 data points. And what we're going to try to do is we're going to try to break this out into two parts. Part because of individual differences and part of it due to group differences. Okay? I'm hoping I make sense here. Okay, so let's let me just try to show this graphically what I'm trying to do, and then we'll work out the equations for getting these things. Okay. Okay, so I'm gonna create a kind of a dot plot here. Oops. So let's, I don't know if I can, I'm just trying to make a grid here to kind of get this approximately reasonable here. All right, so I'm going to just put dots. So I have on diet 1, so this will be diet 1, diet 2, diet 3, and this will be all of them together. So on diet 1, I have a lamb that gained 8 pounds, a lamb that gained 16 pounds, and a lamb that gained 9 pounds, okay? And diet 1's group average is 11, which is right here. So that's its group mean. Under diet 2, we have a lamb that gained 9 pounds, a lamb that gained 16 pounds, a lamb that gained 21, a lamb that gained 11, and a lamb that gained 18. Its group average is right here at 15. Under diet 3, we have a lamb that gained 15 pounds, a lamb that gained 10 pounds, a lamb that gained 17, and a lamb that gained 6. And its group average is right here at 12. Okay, so then just kind of putting all of these dots together, okay, we have that, and the grand mean is at 13. So I'm going to just kind of make a big red bar to indicate this is my grand mean of 13. Okay, and so the total variance can be thought of, you know, as we could look at this data point, the 8, okay, and we could say, all right, so its squared distance from the mean would be 13 minus 8. So data point 8. So y equal to 8. Let's see. And y grand bar is equal to 13. So as far as this data point goes, the amount it contributes to the total sum of squares would be 8 minus 13 quantity squared, right? So it contributes a total of 25 to the total sum of squares. Is that okay? All right. And what we are going to do is we're going to say, okay, well this point 8 units away, okay, there are two parts to it, okay? Part of it is the fact that its group is its group average is 11, okay? And so we're going to break apart this total distance of 5 into, well, the group average is 11, and this individual difference is this lamb gained less compared to the rest of his group, okay? And so we would say there's a difference between y bar and y double bar, and that's a unit of, there's 2 units of difference there, and then on top of that, and another 3-unit difference there, okay? So we're going to break apart this into this and this, okay? So we're going to say, you know, 8 minus 13 is going to be broken out into 11 minus 13. So this is the difference between the group average group mean and grand mean. Okay, plus 8 minus 11, which is a difference between the individual and the group. Is that okay? So this is what we're going to try to do. Okay, and so I'm going to create a kind of a formula for the we're going to have kind of source of variation. We have the total variation, or the total sum of squares, and then one of the sources will be sum of squares due to the group. Okay, so basically the fact that the group is different from the grand mean, we are going to say, okay, this data point of 8, its group mean was 11. Okay, so what we're going to say is we're going to take the difference between the group mean and the grand mean, okay, and we are going to square this difference. Okay, the sum of squares due to the group is going to be the group mean, the fact that it's different from the grand mean. Okay, and we're going to do this for all of the points within the group. Okay, and so if I do this for all 3 points, all 3 of them will have the same difference of 11 minus 13, right? Because they all have the same group mean. So I can just take y bar minus y double bar and multiply that by n. Okay, and I just want to make sure I put the n as either before or after. So I can just take this difference and multiply it by how many numbers were in that group. Okay. Meanwhile, this one, if we look at its group mean is 15, so I would do 15 minus the grand mean of 13, and all 5 data points would have that same thing. So we would still be y bar minus y double bar squared times the number of points in the group. And we would just add this for all groups. Okay. The sum of squares due to group is basically the difference between the group mean and the grand mean squared multiplied by the number of points within the group added across all groups. Does that make sense? Okay. And then we will have the sum of squares due to individual differences, or this is called the sum of squares residual. Okay, and so here we would say, okay, now that we've accounted for the fact that the group means are different from the grand means, there's still a difference between individual data points, okay, and their group means. So it would be y minus y bar, okay, and we would square this, and then we would have to do this for all of the data points within that group. Okay, and then if I did it for all of the data points in here, I would have to still do it for all of the groups. So this is the difference between each data point and its group mean. We're going to square that difference, and we're going to add that for all of the data points within a group and do it for all of the groups. I don't know, maybe I should write that down. So each point and the group mean okay, and then we will say summed done for all points in a group and done for all groups. Is that okay? Kinda? All right. So let's just kind of see if this works out. Well, I mean it does, but I will demonstrate it. Okay. So so let's take a look at just group 1. Okay. So we'll look at group 1. Okay. So the sum of squares total for group 1, or from group 1, will be 8 minus the grand mean of 13 squared plus 16 minus the grand mean of 13 squared plus 9 minus the grand mean of 13 squared. So this will be each data point minus the grand mean squared. So I would end up getting, so this ends up being 25 plus 9 plus 9 minus 13, 16. And so I would get, what is this? 25 plus 9 plus 16. Sum of squares total is 50 there. Okay, so that's the total sum of squares. All right, so let's look at the sum of squares from the group, which is n times the group mean minus the grand mean squared. Okay, so the group mean is 11, and we subtract off the grand mean of 13, and we would square this, and we have 3 data points there. So we have 3 times 9, we have a total of
3 times 4?
Oh, I'm sorry, 3 times 4. I was like, something doesn't seem quite right. Okay, 3 times 4, and we have a total of 12 here. Is that okay? So this is the sum of squares due to the group. Okay, so this would be all of the red arrows kind of squared, and then we look at the sum of squares residuals. Okay, which is each individual point, its difference from its own group mean added up. Okay, and so right now I'm just doing it for one group, but for the total you would do it for all of the groups and add them all together. Okay, and so here we would say, okay, 8 is different from its group average of 11, and then 16 is different from its own group average of 11, and 9 is different from its own group average of 11 as well. Okay, and so here we would have 8 minus 11, so 3 squared, 16 minus 11, 5 squared, and 9 minus 11, 2 squared. So I have 9 plus 25 plus 4, and I have 38. Okay, and so indeed 50 is equal to 12 plus 38. So we've broken out the total sum of squares into these subcomponents. The sum of squares due to the fact that the group is different from the grand mean, and then the fact that individuals are different from their own group mean. Okay, and so you know, it worked for group 1, it's going to work for group 2, and it's going to work for group 3, and we would have a total sum of squares, and we would have a total that's due to the sum of squares group and the sum of squares residuals. Okay. Okay, there is, so this sum of squares residual, however, this requires that we have the individual data points, okay? And oftentimes, it might not be provided to us, okay? And so we can, there's a workaround where if we don't have the individual data points here, okay? And so, so the sum of squares residual is the difference between each point and its group average squared. So the sum of squares residual is each data point minus its group average squared, and we add this up, okay? But this requires each data point y. Okay, and so and which might not always be available. Okay, and so to kind of work around this, we'll count on the definition of the group, or a sample's standard deviation. Okay, so the sample standard deviation, or sample variance, so actually, yeah, let's just do sample variance, which is s squared, is equal to the sum of each point y minus y bar squared divided by n minus 1. Okay, so this is the definition of sample variance. Okay, and so what do we notice here? Oh, I'm sorry, and this was a double sum here. Well, we notice that sum of y minus y bar squared is right here in the numerator. Okay, and so this leads us to the fact that n minus 1 times s squared is equal to this part, y minus y bar squared. Okay, and so we're going to just plug this into here, so we'll have our total sum of squares residual. So plugging that in, we get sum of squares residual equal, doing this for all groups, n minus 1 times the sample variance added up. Okay, so add up for all groups. Okay, and so just kind of flipping back to the previous slide, we had the standard deviation 4.359. If we did s squared times n minus 1, so s was 4.359. So s squared times n minus 1, which was, there was 3 in that sample, minus 1 times 4.359 squared. I think because of rounding, it'll be just ever so slightly different from the number 38, but 4.359 squared times 2 is, 38.001762. So this is also equal to 38. Okay, so this is compared to the previous slide. Okay, where we figured out the exact sum of squares residuals. Okay. Okay, and so again, so with Anova, we are breaking out the total variance expressed in sum of squares into the two parts. Part of it due to the fact that the groups have different averages, and part of it due to the fact that individuals are different even within a group. Okay. Okay, and so we put this all together in our Anova table. Okay. So the Anova table. Okay, and we have what we call the source, and basically what we mean by it is source of variation. And we might call this between group variation. And then within groups, or the residual. Okay, and then we have the total. Okay, there's a column that we create for degrees of freedom, which I'll explain in just a bit, and then we have kind of the sum of squares, SS. Okay. Then we have mean squares, MS. And then the last will be our F ratio. Okay, so the sum of squares between the groups is, we said, we're going to take each group average and subtract off the grand mean, square that difference, okay, and we do it for all of the points, the n points within a group, and we add this for all of the points. Okay, the sum of squares within a group can be simplified, is really just y minus y bar squared done for all of the points within a group and done across all groups, which is equal to n minus 1 times s squared for all of the groups. And then the total sum of squares is each individual point minus the grand mean squared done for all points in groups and done for all groups. Okay. But usually we never really bother calculating the total sum of squares, because these two things will add up together, and so usually we just figure this out and we figure this out and we just say the total sum of squares is going to be this, because a lot of times we don't have the individual data points. So this is like star, we don't really bother with this one. Okay, and then the degrees of freedom here between the groups is number of groups minus 1. Okay, the book uses the symbol I minus 1. I'm not entirely sure why I became the number of groups. The total degrees of freedom is number of points minus 1. So with 12 data points, we would have 11 degrees of freedom total. And then the number of degrees of freedom within the groups is basically this plus this has to add up to this. And the way we make that work is number of points minus number of groups. Okay. But, you know, in the future, well, I don't know about in the future. In this class, we're really only doing one-way ANOVA. But a lot of times, the residual degrees of freedom is just the number of degrees of freedom left over after you've accounted for all the degrees of freedom that exist in the other sources. Okay, and so it's really just this plus, you know, whatever degrees of freedom plus the residuals has to add up to the total degrees of freedom, which is always going to be kind of the total number of data points minus 1. Okay? The mean squares is kind of the sum of squares that can exist for each degree of freedom. I know that's a little bit of a weird concept here, but if you think of the way we calculated variance, is we did kind of the total sum of squares and we divided by n minus 1, right? And so we could think of the mean squares here as, you know, like kind of the total variance, which is like you take this and we divide by n minus 1, and we're basically doing the same thing here. So it's just the sum of squares divided by the degrees of freedom. Okay, sum of squares divided by degrees of freedom, the mean squares. So it's kind of how much of the variance can be attributed to each degree of freedom, really. Okay. And then the way we test to see if the amount of variance that exists between the groups is significant or not is we take a ratio between the mean squares here and the mean squares of the residuals. Okay, so we say, you know, is the amount of variance that can be attributed to group differences, is that large compared to just the amount of variance that exists between individuals? Okay, and so this is the mean squares kind of between, or mean squares of the group divided by mean squares residuals. Okay, and there's no F ratio for the residuals themselves, because you would, or I guess it would just be 1, because you're always just comparing, you know, is the amount of variance that can be attributed to this particular source of variation, the fact that the groups are different, is that large compared to the amount of variation that exists between the residuals. Okay. Is that so far so good? Okay, and so if we were to create an Anova table for our data set here, okay, so we'll make the Anova table. So we have the source, the degrees of freedom, the sum of squares, the mean squares, and the F. Okay, so the source is between the groups, or basically the diets, and then we have the residuals. Okay, we have a total of 3 diets, so we will have 2 degrees of freedom. We have a total of 12 points, so we have 11 degrees of freedom total, which leaves us 9 degrees of freedom available for the residuals. Okay, the sum of squares due to the diets will be, I'm probably gonna have to move these things here. Okay, so we're gonna have 11 minus, so we have the grand mean equal to 13. So 11 minus 13 squared times 3 plus 15 minus 13 squared times 5, and 4 times 12 minus 13 squared. Okay, so what is that? 3 times 2 squared, so 12 plus 15 minus 13 is 2 squared, so 4 times 5 is 20, and 12 minus 13 squared is 1, times 4 is 4. So we have a total of, what is this, 36? Okay. So our mean squares is going to be 36 divided by 2. And 18. Okay. All right. The residuals. Okay, I would do n minus 1 times s squared. So I would have 3 minus 1 times 4.359 squared plus 5 minus 1 times 4.950 squared, and 4 minus 1 times 4.967 squared. Okay, what is that? Okay, so 2 times 4.359 squared plus 4 times 4.95 squared plus 3 times 4.967 squared. Okay, 210. I think it's a tiny bit over 210 because of rounding issues, but overall we have 210. Okay, and so the mean squares here would be 210 divided by 9. and I get 23.333. Okay, so our F ratio would be 18 over 23.33. Which is equal to 0.7714. Is this okay? The creation of our Anova table. Okay. All right, and so is this significant or not? Well, this is our test statistic. Our test statistic is this F value, and we would look this up in a F reference table. Okay. I don't feel like trying to explain where the F table comes from. It's the distribution of basically a t, like the ratio between two t distributions. I don't know. Basically, so Anova was developed by Ronald Fisher, who's like, as far as statistics goes, he's like the grandfather of modern statistical methods here. And so he developed this this test, and it depends on kind of, and the theoretical part depends on the ratio between two t distributions and their respective degrees of freedom. You know, I think from a practical standpoint, it would suffice just to show you how to look this up in an F table, and it's fine. And I'll just say, just trust me that the mathematical theory works out. I'll also just do a quick demo on how this might look like on a computer, because probably, to be honest, nobody calculates Anova, even one-way Anova, by hand. We just throw things at the computer and say, please do the Anova for me. But it is useful to learn how to use the F table. In your packet of tables, I have not given you the F table. In the actually in the 5th edition of the textbook, they cut out F tables completely, and in the 4th edition of the textbook, they have F tables, but there's like 10 pages of it. The thing about the F table, so let me just write this down. We have F is equal to 0.771, and the F comes from a ratio between 18 and 23.33, okay? And so we actually have 2 degrees of freedom associated with F. We have a numerator and a denominator degrees of freedom, okay? So we have numerator df equal to 2, and denominator df equal to 9, okay? And our F is equal to 0.7714. All right. And so what we would do is we would find in our table, so I'll show you what it looks like in the 4th edition, the F table, and again, there's like 10 pages of this stuff. Okay. So in the 4th edition, let's see. Okay, so it says Table 10, critical values of the F distribution, and there's one page for numerator df equal to 1, a page for numerator df equal to 2, a page for numerator df equal to 3, so on and so forth until there's, you know, numerator df equal to 10. So in our case, we would go to numerator df equal to 2, find the row that says denominator degrees of freedom 9, and we would look up 0.7714. We would say, oh, 0.7714 is smaller than this number 1.93. Therefore, the associated p-value is greater than 20%. Okay. Does that feel okay? Huh?
What is that probability?
This is the probability that, so yeah, sure, I'll write this down on our, okay, so we would say, okay, we would have numerator degrees of freedom equal to 2, and then denominator degrees of freedom equal to 9, and we would say 0.7714 is here, so therefore our p-value would come from over here, and so we have the relevant p-value greater than 20%, okay? So if you recall, our null hypothesis was basically that mu1 is equal to mu2 equal to mu3, or we could also write the null hypothesis saying that each group, the effect of each group was basically nothing, that the 3 diets really had no effect on weight average. And so we were saying, so this basically says if the 3 diets had no effect on weight gain, okay, then the probability that my sample of data would end up having basically this split of variance, okay, the where we could attribute, I forget what the numbers were, basically 36 to 36 of the sum of squares to the groups and 210 to the within diets. So basically, if the diets had no effect, then the probability that I end up getting this particular split in the variance by random chance is over 20%. Okay, so then the probability that you know, we get, you know, a quote split of variance like our data's, or something more extreme, is over 20%. Okay, so this kind of data split could happen, or variance split could happen quite frequently just from random chance. Therefore, we would say we do not have evidence that that the diets had any effect on weight gain. Okay, so and I mean, the diets could have an effect on weight gain. It's just that, you know, we only looked at 12 lambs, so that may just not be enough data. Maybe if we looked at 1,000 lambs on 3 different diets over lots of time, we would see you know, a more pronounced difference. But with just 12 lambs, we don't have evidence that the diets really do anything. Okay, is that all right? This F table is quite unique, I would say. Most of the time, if you go on the internet and you just say, or most other textbooks, so I feel like I've been saying like other textbooks do this. I really do like this textbook, but it does a few things that are quite, I would say, unique compared to a few of these things. Okay, so if you were to look up an F table, most of the time your F table would look something like this. Let me see if I can, this is like really hard to see, okay? And so it will say something like F distribution alpha equal to 0.05, okay? And then you would have degrees of freedom across the top and degrees of freedom down the side, okay? And so what we would do is we'd say, oh, we have 2 numerator degrees of freedom and 9 denominator degrees of freedom, and the number it appears here is 4.2565, okay? And basically it's saying in order for your F ratio to be significant, it has to be bigger than 4.25, okay? And so we would just say, oh, our F ratio is 0.77. We compare that to 4.25, and we'd say it's smaller than that, therefore it's not our thing is not significant at the 5% level, and it would just be that, okay? If your F ratio ended up being 7, you would say it is significant at the 5% level. And so really we just have, you know, our tables like, oh, we can say our p-value is greater than 20%, or our p-value is, you know, between 5% and 10% or something like this. This is just kind of this single number, and it says, is it significant at the 5% level, or is it not significant at the 5% level? And that's what you have, yeah.
The F ratio is always less than 1. Like the difference within groups is bigger than between groups. Is that ever going to be significant?
If the F ratio is less than 1, I'm trying to think if, I don't know. I guess at infinity degrees of freedom, there might be a point. I don't really know. Probably not. Okay, I feel like the F ratio has to be fairly
The
big.
variance is bigger within a group than between.
Yeah, I'm just trying to think if there's ever a scenario where it is, and yeah, I think you're right. Safe to say that if the F ratio is smaller than 1, it will certainly not be significant, at least at the 5. Wow, I have a hard time saying ever, but yeah, I mean, so I'd say, you know, if a textbook includes an F table, it generally looks something like this, okay? And so maybe it's worth including something like this in our notes as well. I don't know where I would fit it. Okay, never mind. But I don't know. Is that okay that I'm not putting it in the notes? Okay, so we would just, but you would just look this up and you'd say, oh, okay, my F ratio ended up bigger than this, so it's significant. My F ratio is smaller than this, it's not significant, okay? And I'd say most textbooks work kind of that way. I think if you look at any if you just search F table on Google, these are the types of F tables that get printed. I'd say it's quite unique that our well, and I understand because our textbook needed 10 pages of F table, and most other texts are not so generous with their F tables. Okay. If you'll indulge me, I'm going to show you how the Anova is done in R, okay? And so, you know, there's a few ways we could do this. So, you know, perhaps you have gathered data, and oh, look at this, my Excel updated. And so, you know, you would have something like diet and weight gain. Okay, how do I zoom here? Okay, okay, show tabs and commands, and then view, zoom, 200, I don't know, whatever. Okay, so there we go. Oops. I don't know what that is. How do I undo that? Okay. All right, and so I'm going to put diet A, and say the weight was 8, 16, and 9, and then under diet B, we have these weight gains, 9, 16, 21, 11, 18. And then weight gains, or diet C, the amount of weight gain was 15, 10, 17, and 6, okay? And the reason why I'm choosing to use A, B, C, and C rather than diets 1, 2, and 3 is because when you import this into R, if it sees 1, 2, 3, it's going to think you're talking about numbers. And it's going to think like diet 1 is not diet 1, but you have 1 of something, and you have 2 of something, and you have 3 of something. And that diet 3 has 3 times more than diet 1, and or it has 1.5 times more than diet 2, or something like that. And so you would have to tell R, oh, you know what, these aren't numbers, these are actually just labels, okay? But if you give it the letters A, B, C, it understands, oh, these are labels, and it's not that C has more than A or something like that. It just understands that as labels. You could label it diet 1, 2, and 3. That's no problem, but you would have to specifically tell R, treat this as labels and not as numbers here, okay? And so R prefers text files, and so we'll just call these lambs. Okay, and then where am I going to save this? I'll just save this onto the desktop. Okay. Okay, lambs.csv. Okay, yeah, that's fine. Okay, and then so in R we would do import data set from a local file, and we'd go to our desktop and we'd say lambs.csv. Okay. And it says, oh, okay, you got diet and you've got weight gain. You know, what do we want to call this thing? Lambs. Does everything look good? Row names, yeah. So, you know, you've already done this with like the blood pressure data or something like that, right? So you've got this, okay? Strings as factors, that's fine. And we click import, and it says here we have lambs, okay? And so we can, you know, we can just say like, if I ask for, lambs $, weight gain, we have this, and we can say, you know, what is the mean of lambs $, weight gain? And it says that the mean is that, and if I ask for the variance, it says something like that, okay? And if I do the variance squared, which would be our sum of squares 500, that's, what am I doing wrong here? Oh, no. Wait, the variance of lamb's weight gain. Yeah, variance is 22 point. Oh, okay, I'm sorry, not squared. Variance times 11 would be our sum of squares total, right? N minus 1. So this is our total sum of squares. Okay, to do the ANOVA, okay, I'm going to just create something called results, and we would do AOV. And what I want to do is I want to explain weight gain. Explained by diet. Okay, so I've got weight gain tilde diet, and the data I want is lambs. Okay, and that's it. And then I could just say print out the results, and it says this. And really, what's of interest to us is summary of the results. Okay. And this is what it gives us. So this is the exact Anova table that we generated by hand, right? And it says degrees of freedom is 2, 9, sum of squares 36, 2, 10, 18, 23.3. The F value is 0.771, and the P value associated with this thing is 0.491. Okay, and so R makes it very easy to do Anova. Just using the command AOV for all of this, okay? And that's that. So yeah, the key, I guess the key would be don't create, so in our textbook it creates a table with 3 columns of data, and here you want to just have basically all of the measurements in one column, and then kind of the labels for the groups in another column. So you want to make sure your data is recorded in this form, and you can and you can perform one-way ANOVA quite easily. So again, the relevant command here would be, store the results, and we're going to do AOV for analysis of variance, where you want to explain weight gain. That's our response variable, as explained by the different diet, and then the data is coming from lambs here. Okay, and then we get our summary table from here, and then it prints it out right there. Okay, why don't we take a break here, and when we come back, I'll talk about some of the other forms of ANOVA, some things to keep in mind for experimental design and whatnot. Okay, so we'll